In this discussion video, we're going to talk about neutralization reactions and a lab technique called titrations. So what we're going to be doing is we're going to be using the idea of acids and bases to look at what a neutralization reaction is and how we can actually perform those neutralization reactions in lab. So the first thing that we want to talk about is the neutralization reaction itself. So we did talk about neutralization reactions when we did types of reactions and we talked about double replacement. A neutralization reaction is just a double replacement reaction between an acid and a base, and it produces a salt and water. So whenever you have an acid, which is going to start with an H, and you have a base, which is going to end with OH, you're going to create a salt and you're going to create water, H2O. So if you remember when we balanced equations, some of the tips that you were given when you were balancing is that you can write water as HOH to help balance the H's and the OH's. That was an acid-base reaction. Now when we say salt, we do not mean NaCl. NaCl could be one of the salts, but the definition of a salt is an ionic compound that's formed from the anion of the acid. So the anion is going to come from the acid because it reacts with H+. So the anion of the acid and the cation of the base, those we're going to crisscross charges and we're going to form a salt. So when we talk about a salt, it's an ionic compound that's formed from the anion of the acid, cation of the base. So what we're going to do is we're going to look at this first example. This just says to complete the following neutralization equations, right? The molecular equation with states of matter. So what we're going to have to do is we're going to have to think about our products, and we're going to have to think, is the salt soluble in water? Because if it is, it's aqueous. If it's not, it's going to be a solid. So we're going to look through each one of these. We're going to focus on the molecular, but I'm also going to show you how to look at the net ionic.
Okay, so in example 1, it says to complete the following neutralization reactions. So each of these three reactions are acid-base reactions. So in A, we have HCl, which is hydrochloric acid, reacting with NaOH. So remember that neutralization reactions are just double replacement reactions. So you take your positive ion from the acid, positive ion from the base, and switch them. So these, the H plus and the Na plus, are going to switch places. So that means I'm going to have Na plus, let's write this up above, Na plus 1 is going to combine with Cl. Now remember, whenever you write a new formula, you have to look at charges and you have to crisscross. So I'm going to have Na plus, Cl minus, so that's just going to give me NaCl. Then we're going to have H plus combined with OH minus. Well, H plus and OH minus makes H2O, makes water. Water is always a liquid. Notice it says to include states of matter. So water is always going to be our liquid. So then we have to think about our solubility rules. Now, here's a quick way that you can remember some of these ionic substances. Remember that anything with potassium, nitrate, NO3 minus, ammonium, NH4 plus, or sodium, anything with these four ions is always soluble. Anything other than that, we would have to look at our solubility rules. So NaCl has Na plus, so it's going to be soluble, which means it's AQ. Now double check, make sure it's balanced, 1 Na, 1 Cl, 1 H, 1 OH. So remember, an easy way to balance this is to treat it as HOH. So there's A. Now this is the molecular equation. If this asks for the net ionic equation, you have to break up anything that is a strong electrolyte that is aqueous. So a strong electrolyte, those are strong acids, strong bases, and soluble ionic salts. So we would have to look at the solubility rules to figure out if it's a soluble ionic salt, but strong acids and strong bases always break up into their ions. So if I were to break this up, if I wanted to look at the net ionic equation, I would break HCl up into H plus and Cl minus. I would break NaOH up into Na plus and OH minus. I could break NaCl up into Na plus and Cl minus, but water will stay together. So here's why I broke these up. HCl is a strong acid, dissociates completely. NaOH is a strong base, dissociates completely. NaCl is a soluble ionic salt, breaks up completely. The only state of matter that you can break up is aqueous, so solids, liquids, and gases always stay together. Here's my complete ionic. What would I have to do to make it net ionic? Cross out your spectators, so Cl minus, Na plus. So my net ionic equation for this is H plus OH minus yields H2O. So I have H plus aqueous, OH minus aqueous yields H2O liquid. Now that's if it asked for net ionic. This is just asking for the molecular equation, so we can leave it like we had up here. But for example, in B, this is a strong acid. HNO3 is a strong acid. MgOH2, if you look at your periodic table, magnesium, that's a weak base. So if we were actually writing the net ionic equation, this stays together. Even though it's aqueous, this stays together. So we would break HNO3 up into H plus NO3 minus, MgOH2 stays together, and then we would look at our products. So let's look at our products in this. So this is a double replacement reaction. So you always make water, H and OH. Now it doesn't matter what order you have it in. I'm going to leave this as HOH for now to help us balance. Then Mg will combine with NO3 minus. Mg is plus 2, NO3 minus, well, NO3 is minus 1, so when you crisscross, it's MgNO3 2. So I have water, and I have magnesium nitrate. Now water's a liquid. Anything with potassium, nitrate, ammonium, or sodium is always soluble. This has nitrate. It's aqueous. So now let's balance this before we do anything else. This is why you can write water as HOH. 1H, 1H, 1OH, 2 OHs. Put a 2 out front there, 2 NO3s, 2 NO3s. So this is balanced. If you want to rewrite your products and make it say 2H2O liquid, that's fine. But this is what your balanced molecular equation would look like. If it wants your net ionic, you would break up HNO3 into its ions. You would break up MgNO3 2 into its ions. But this isn't asking for net ionic, it's just molecular. Okay, so then C, we have aluminum hydroxide and we have sulfuric acid. So if we're writing our products, aluminum, so the cation from the base is going to combine with the anion from the acid. So I'm going to have Al, which is plus 3, SO4 is minus 2. So when I crisscross, I get Al2, SO4, 3. And then I'm going to have H and OH. I'm going to have H2O. I'm going to leave it as HOH for now. Helps me balance. So I have 2 ALs. I only have 1 AL here. I'm going to put a 2 out front. I have 1 SO4. I have 3 SO4s. Now I'm going to look at water. I have 6 H's and I have 6 OH's. I only have 1 H and 1 OH, so I'm going to put a 6 out front. Now it's balanced. All right, so that's our molecular equation. If it wants net ionic, you break up anything that's a strong electrolyte. Your strong electrolytes are strong acids, strong bases, and soluble ionic salts.
So this second example says, what is the acid and the base that will create the following products? So this is having us look at the products and go backwards to figure out the reactants. So when you're looking at your products, remember that the cation comes from the base, the anion comes from the acid. So really we just have to go backwards. We know that Ca is going to mix with hydroxide to form the base. NO3 minus is going to react with or combine with H plus to form the acid. So if you crisscross your charges, your acid will be HNO3, so nitric acid. Your base will be CaOH2, so calcium hydroxide. So remember, whenever you write a new formula, you have to look at charges. You have to crisscross charges. So you'll have HNO3 plus CaOH2. Then go through and balance the equation. So remember, you can rewrite this as HOH to help you balance. You can balance the H's, you can balance the OH's. So the next thing that we're going to look at is the actual lab technique that's called titrations. So a titration is a method to find the concentration of an unknown. Now in lab, we will be looking more than likely at the concentration of an unknown acid. And what you do is you will take an acid and a base. Typically your base is going to go into the burette. Your acid is going to be down here in this Erlenmeyer flask. And what you're going to be doing is you're going to be neutralizing it. So you're going to put it through a neutralization reaction. And you can use the information, you can use the volume of the base and the concentration of the base to figure out the concentration of the acid. And so what we're going to do is we're just going to watch a quick video on what a titration setup looks like in lab. So when you do this in lab, you have an idea as to how the setup will look.
A titration is a controlled acid-base neutralization reaction. 20 milliliters of hydrochloric acid of an unknown molarity is added to a flask. 2 drops of indicator dye are added to the acidic solution. This indicator dye is clear in acidic solution and pink in basic solution. The burette is filled with a sodium hydroxide solution of known strength and an initial reading is taken. The base is added to the acidic solution until the solution stays a slightly pink color. At this endpoint, a final reading is taken. The moles of base added equal the moles of acid present. This same reaction can be followed using a pH meter instead of an indicator dye. Initially, the pH changes very little as base is added. Suddenly, the pH changes rapidly as the endpoint passes. The solution quickly becomes very basic, and again, the pH changes very little. The endpoint occurs at this middle point on the curve.
Okay, so when we are thinking about titrations, we want to look at what is needed. So there are 3 things that we typically use during a titration. We use what's called the standard solution, which is also called the titrant. This is what actually goes in the burette. So a standard solution means that you know the concentration. So typically this is going to be a strong acid or a strong base, which means it completely dissociates, breaks up completely. So when you have a standard solution, you know the concentration of that. So maybe it's 0.1 molar NaOH. The analyte is what is in the Erlenmeyer flask underneath the burette. This is what you're analyzing. This is the solution that has an unknown concentration. So this is what you're trying to figure out the concentration of. That's the whole point of a titration, is to figure out the concentration of an unknown. And then an indicator, and you should have seen an indicator before. Phenolphthalein is what we used in one of the labs already. An indicator changes color when the pH changes to show if a solution is acidic or basic. So phenolphthalein is clear in an acid, and once phenolphthalein is in the pH range of 8 to 10, it's going to turn pink. There are other indicators that you can use as well. You can use methyl red, bromothymol blue. All of these indicators will actually change color at different pHs. So the purpose of a titration is to figure out the volume that was used out of the burette and to try to calculate the concentration of an unknown. Now, when we're doing a titration, there are 2 points that we can look at. The end point is the point in a titration when your indicator changes color. So when it says the end point had a volume of 50 milliliters, that was when your indicator changed color. Now the equivalence point is what we really care about. Now a lot of times the end point and the equivalence point are the same on a titration curve, but the equivalence point is when your moles of acid equals your moles of base. So this is when they are stoichiometrically equivalent. We can do stoich. We can use the mole ratio. So if it's a 1-to-1 ratio, moles of acid equals moles of base. So our concentration of H plus we can use to find concentration of OH minus or vice versa. So at the equivalence point, we always say moles of acid equals moles of base. Then that lets us calculate concentration. So the way that we use a titration to determine concentration is that we use this ratio at the equivalence point. Now, if your mole ratio is 1-to-1, so if it's HCl and NaOH, 1H, 1OH, you can use this equation down here at the bottom. And this should look similar because this looks like the dilution equation that we used. So you have MAVA equals MBVB. Notice it's capital M, so it's the molarity of the acid times the volume of the acid equals molarity of the base times volume of the base. The reason that this works the way that it does is because molarity times volume equals moles. And so if moles of acid equals moles of base, we can do molarity times volume equals molarity times volume. And typically, you're going to be looking for the molarity of an unknown. So you should have the volume of both and the molarity of at least one of them. So what we're going to do is we're going to look at this last example, and it's asking for the molarity of the hydrochloric acid if you have 30 milliliters of the acid titrated with 60 milliliters of 1.5 molar NaOH. So we'll take a look at this example as well.
So in example 3, it's asking us to find the molarity of HCl. So let's check and make sure we have a balanced equation. So everything here is balanced. Because this is a 1-to-1 ratio of acid to base, I can use MaVa equals MbVb. Molarity of the acid times volume of the acid equals molarity of base times volume of base. I am trying to find molarity of the acid, so that's going to be my unknown. Volume of the acid is 30 milliliters. Now, as long as your volumes are in the same unit, you can keep them like they're given. So 30 milliliters. Molarity of the base, 1.5 molar. Volume of the base, 60 milliliters. Notice they're both in milliliters, so that's fine. And so what I can do is I can solve for Ma. So divide both sides by 30 milliliters. So notice that cancels out my milliliters. What we're going to get for the molarity of the acid, 60 divided by 30 is 2. 2 times 1.5, we get 3.0 molar HCl. And again, we can use that because it's a 1-to-1 acid to base ratio, so we can use this equation.